Hello everyone. Hello everyone. Okay, so we will start with the next part of the MOSFETs. Okay, so I decided to go with the basics only to arrive at the formulas, whatever is there. So we'll arrive at the formulas of MOSFETs, starting from the basics. Last time we saw the MOS capacitor, we saw the accumulation, depletion, and inversion layers, right? So now we will move from there. So the structure you see here is the view of a MOSFET. Okay, so you can see that what I was explaining in the last class, that there will be a gate terminal, a source terminal, a drain terminal, right? And the application of voltage actually defines which will be your source, which will be your drain. So source basically injects the carriers and drain accepts the carriers. So source will inject electrons and it will move to the drain. So if the electron is moving from source to drain, your current will move from drain to source. And if the holes move from source to drain, then the current will also move from source to drain. So holes will move when it is a p-type channel, therefore making it a p MOSFET, and electrons will move from source to drain and therefore current from drain to source in N channel MOSFET. Okay. Okay. So now from here I am referring to the book of Razavi for this part, Microelectronics by Razavi I am referring. Okay. So now let me start with this. I'll explain the figure later, a bit later. Okay. So we will first have a small throwback, okay, to the concepts, a small throwback to the concepts. Suppose there is a semiconductor bar, okay, there is a semiconductor bar and I want to find the current flowing through it. So the current will obviously mean that there is some charges which are in motion, right? There is some charges moving with a velocity v, okay. So if I say that in this semiconductor, okay, I take a section like this. Okay, I have taken a section like this and I say that uh, this distance is v meters. This is v meters. Okay, this is v meters, and therefore the velocity with which the carriers will move will be v meters per second. Okay, I am taking per second. Okay, so in 1 second, this is what the v meters is, what is the distance your charge carrier will move. I'm using the word charge carrier, it can be electron or hole. Okay, so therefore and now if I say that the mobile charge density, the charge carrier that will move from these v meters, they are having density as qd. Okay, qd is nothing but what? Charge per unit area. Charge per unit meter. So in that v meters, qd is your charge density, and therefore this is in coulomb per meter. Okay, so now if you multiply qd into v, you will get what? Coulomb per meter multiplied by meter per second, and therefore you get a unit of coulomb per second, which is nothing but amperes, and therefore I current can be given as qd into v. Please note that you would have studied this. I is equals to q by t, which is what I have written here, charge per unit time. Here I am terming qd as a density, okay, mobile charge density. I'm terming it as charge density, okay, and therefore the unit is different. It is coulomb per meter. Okay, so now this is what a throwback we had. We are having this throwback that we will be using this equation. That's why I wanted to just revise this once. Okay, So keep this equation in mind. Now let's come to the MOS cap arrangement that we had. So if I say that here I have applied a VG, here I have applied a gate voltage, okay, and rest of the terminals are grounded, which is given by this circuit here, right? So we know that on the application of gate voltage, if it is in inversion region, we will be having a channel formed, right? I'm putting it in green, if you can see. Huh? So let me put it in some other color because there it is unable to. So this is the channel that will be forming depending on the polarity. So let's say whatever the polarity is, it's a p substrate, so n channel will form, so it's a positive polarity, right? So the channel will form. Now okay, so when the channel will form, what will happen? There will be a flow of current if I now put any voltage in D or S. The gate voltage will actually help in forming the channel, and then your electrons will flow according to whatever drain to source voltage you are applying. Okay, that will set it in motion. Now I want to find the charge density here. Okay, I want to find the charge density in that channel. So what will be the charge density in the inversion layer? So when VGS is greater than the threshold voltage of the MOSFET, then only the channel will form. This is the condition for inversion, right? So inversion charge. So some of you were asking for, I got a mail asking for notes. So I cannot upload anything because this is all very much rough work. Okay, so that's why I'm not uploading anything. I'm giving you the reference of books. Please go through it and make your own notes, or you can make the notes sideways as you are listening here. You can make it here also. Okay. So inversion charge will be given by, what is charge when there is a cap arrangement? Q is equals to CV, where C is the capacitance, right? So now, so now what happens is the capacitance which is there is actually represented here as COX. This you will see in many places, which is the oxide capacitance. Okay, COX is the oxide capacitance, and it is basically denoted as gate. So I should have shown you that. So let me just make a quick diagram here. So if your MOSFET is like this, okay, then in the depletion region what will happen, that and you have this gate like this, right? So the gate is here and this oxide is here, right? And there is some voltage here, and then this depletion region here is formed. So normally there is one, normally there will be one capacitance which is present, which will be from gate to your oxide. These two will form one capacitance. Remember, wherever there is a metal plate, okay, a conducting plate, two conducting plates are there, there is one capacitance. It forms a capacitor. Okay, so ground is also a conducting plate, and therefore you would have heard this, that if some transmission line is going on, there will be a capacitance between this and ground, right? So basically this is the concept. So the gate, you can see that there will be a capacitance between these two, and this is referred as COX, the gate oxide capacitance per unit per unit area. Okay, gate oxide cap per unit area. So that means its unit will be different, right? It won't be capacitance alone. It won't be farad. It will be something else. We'll see. So gate oxide capacitance per unit area. Now, when the depletion region exists, there is another capacitance here from here to the depletion region, which is called C dep, and at that case actually these two will come in series and the total capacitance is given as Cox parallel C dep. Okay, so I'm not going to that part, that will come in the MOSCAP. So I don't know if it is very much asked in GATE or not. So from where do you want me to repeat, Navneet? So we are looking into the inversion charge and the charge which is due to the MOSCAP arrangement is given as Q is equals to CV, where capacitance C is denoted as, is used as Cox here. Just remember right now that it is a gate to oxide cap that we are talking about, and its unit is not farad, its unit is something else. Okay, farad per area it will be. Okay, so now let's start with Q equals to CV again. So now QD I had written as what? C into V. So this C is due to the Cox, but Cox is what? Per unit area. That means I have to multiply dimensions of the MOSFET here, right? So what we make, we multiply it with W, and this thing, this entire thing is now having the dimension of what? Cap per unit length, because I have multiplied the width of the MOSFET. Okay, so if you come to this, you will see here that this, can you see here, W it is written, width of the MOSFET, right? So basically the Cox is what? Actually Cox is the cap per unit area. Okay, and this will be your channel length. For now this is your channel length L. So basically the total cap is nothing but Cox into W into L. This is your total cap. But here what I am doing, I am checking the QD, right? So we saw that QD is given as I is equals to QD into V. QD is nothing but coulomb per meter, right? It is charge per unit length. Therefore, what we will do when we write QD, we have written C into V. V is the voltage. C we will write as Cox into W into V. Okay, so for those who have joined late, please try to join as early as possible. I normally open the gate around 5 minutes before 4. Okay, 3:55 or 3:56 I start. I open the platform for you guys, and 4:05, around 4:05 I start my lecture. So if you join late, you won't be able to understand. So I will quickly say from where I had gone. So we were just seeing a semiconductor bar, and we saw that the current given in the semiconductor bar in a V meter cube, okay, I should not say cube, in a V meter length, is current is given by QD into V, where QD is charge density denoted as charge per unit length, and V is the velocity, okay, that particular distance per unit second, and if you multiply it, you will get the current from that particular V meter distance. Okay, so we are going to use this to find the charge of the MOSFET. So now I went to the inversion layer, and we saw that it is W and L are the dimensions of the MOSFET, and normally we talk about oxide capacitance. So oxide capacitance is always given as capacitance per unit area, and therefore the total cap C will be nothing but Cox into WL. But here we are, what we are doing, we are checking charge density. So this will have units of what? Charge density is coulomb per meter, right? And therefore you see, if Cox we have written Cox W, this is having unit of what? Farad per meter, right? And then you have voltage, volts. So farad into volts is what? Farads into volts is coulombs per meter. Okay, so like this you should be able to match the units always. This reduces your silly mistakes probability. Okay, So is this clear to all, or anything is there which is not clear? I will write it again, so don't worry. Is this clear? I'm not getting any response. So anyone? Is this thing clear? Anyone else? Chandrasekhar said yes. Okay. So now QD, which is the inversion charge, is given by C into V. C is given as COX into W, capacitance per unit length, into volts. So this V, this is capital V. Okay, this is capital V. This is QD. Okay, fine. Now what is this V? What is this V? Because of which voltage has this charge come? Because of the VGS that we had put, right? So we had put a VG here, okay? And here everything will be with respect to source, let's say. So VGS. And this VGS, when it goes over the threshold, VTH, when VGS is going over VTH, then charge is coming. That means the total voltage total voltage because of which the cap is coming into effect, the charge is coming into effect, QD is coming into effect, is given by COXW into VGS minus VTH. Because this is actually the voltage which is causing that inversion charge, right? So therefore, we arrive from here, we arrive at QD equals to COXW okay. Is this fine? So here everywhere what is happening, that there is a potential 0 volts at source, 0 volt at source and 0 volt at drain. This is what we have assumed. Now suppose there was a non-zero voltage at drain, then what would have happened? So let me just quickly copy this thing again. Okay. So now here you see that, sorry, cannot be zoomed that much. So I hope you guys can see it. So here you will see that if this is the NMOS, N plus, okay, and the gate is here, right? So what is happening? If this is grounded and this is, I have some potential, say VD, and this is the gate, that means here the potential is, sorry,
Can I explain test diagram?
you have
Can
just
I explain
joined, I
test
think.
diagram?
So if I keep on repeating, others will suffer.
Why, ma'am?
So you have just joined, right?
Why, ma'am? Yes, ma'am.
So you should have joined at 4 o'clock. You have joined 23
Yes,
minutes
ma'am.
late. So I have already explained this diagram.
Yes, ma'am. Can another explain, madam?
So please
Yes,
all
ma'am.
of you join at 4
Another
o'clock from
explain,
next
madam?
class. Otherwise, if I keep on repeating, then others will suffer. Okay.
Okay, ma'am.
Everybody's time is important here. You should respect
Okay,
it.
ma'am. My madam, my
Please, I'm
importantly.
explaining it again. So you can mute
My
yourself.
madam, my importantly.
So this MOSFET, you can see that. Yeah. So what is you are not able to understand in the diagram? Can you tell me?
Yes, ma'am.
What is that?
Yes, ma'am.
What exactly in the diagram? Like you are unable to
Diagram.
understand what diagram it is or what?
Starting. Start.
Okay. You can
Starting.
mute yourself.
Start.
So this is a MOSFET, and here I have, if you would have attended the last class, this is the MOSFET with N plus layers. okay, N plus dopings, and here there will be a channel formed when there is a gate voltage. Okay, so basically what is so where was I forgot. Okay, so here is the diagram. You can see here is the next diagram where the source is grounded. Okay, so that means from here it is 0 volts, right? And here I am putting some voltage Vd. That means the potential at every point is now not the same. There will be more potential here and there will be less potential here, right? And therefore the Vg, right, the Vg which is here, okay, the potential difference is more than the potential difference which is here, right? Vg minus Vd. So Vg minus Vd is what is at drain and Vg is at source. Okay, now you can see that, yeah, so if there, so we come across that there is a potential difference. So now we had seen that the charge was given by Vgs minus Vth. That is what we had written. Okay, but now I am seeing that as I move in this direction, which is my direction x, right, and this arrow you can see. So, and we have said that this is the channel length 0 to L, right? L we had seen that it is the channel length. So as I move in this direction, my voltage, which is actually responsible for the inversion charge, will not be Vgs minus Vth always. Agreed or not? It is not always Vgs minus Vth. It is Vgs minus Vth at this point here in the diagram I am marking. Because the gate to this your substrate potential, whatever is there, is 0, right? But as I move in the x direction, what will happen? There is a voltage coming. So that means a voltage is present which is function of the length x, right? So now you can write QD as WCOX VGS minus of V of x minus VTH. So this is your actual voltage. Okay, minus V of x minus Vth, where Vx is the channel potential at x. Now x can be anywhere here. X can be anywhere here down the distance 0 to L. So this is x. This is x. So x can be anything. And at any point I can now find the voltage. Is this clear till here? Any doubts? So I understand if someone joins late, you can ask me question. But if you ask me what is this diagram, then you understand I have to go back to the last class. So I hope that is not an issue. I don't want to waste everybody's time here. Okay. Okay. So this is fine, I guess. Okay. So now what will be current? We saw the current formula, right? Current was given by, where V, small v is the velocity, right? Small v is the velocity. Now ID will be WCOX VGS minus V of x minus VTH into small v, right? So now you see that here Vx is the term which is dependent on x, everything else is constant, right? And we will see what V is. V is velocity, so that also is dependent on x, right? Acceleration is velocity per unit what time, and what is velocity? It is per unit distance per unit time, right? So this is what is dependent on the distance. Okay, okay. So we have studied in semiconductors what is V, what is the velocity. Okay, so what is this velocity? Nothing but the drift velocity. So you would have studied that what causes the, what current causes, what is the current which is there in the MOSFET, what causes the current in the MOSFET. So it is the drift current. There is no diffusion phenomena here. This is the drift current which is causing the current. So that means there is a presence of electric field, right? And drift velocity V is given as mu e, right? One more thing that I missed is, since we are talking about n MOSFET, the channel is due to electrons, the current will have a minus sign, negative, to show the direction, right? And when I'm writing V is equals to mu e, right? And so this is mu n, and then it can be written as minus mu n. E is given as what? dV by dx, right? Till here, is it fine? Okay, so this negative sign is because of electric field. Okay, minus dV by dx. Now you put it in this equation. If you put it in this equation, you will get W mu. I'm not writing n for now, okay, just for simplicity. COX VGS minus V of x minus VTH into dV by dx. Okay, so now what we were saying, we were saying that there was a channel which was going from 0 to x. Okay, and now I have arrived at a small portion of dx. That means if I integrate now, I will get the entire current that is flowing through the channel. So from where to where will I integrate? So id into dx equals to W mu COX VGS minus V of x minus VTH into dV, and you integrate. If here you are integrating from 0 to L, because it is x is going from 0 to L. So what we had seen, from where to where the voltage is going, it is going from 0 to VDS, the complete voltage, right? The drain voltage with respect to source, right? So at source, the voltage with respect to source is 0 only, Vs minus Vs is 0, and here Vd minus Vs is VDS. That is what I have written. Okay, so here it will be 0 to VDS. Now if you integrate it, the equation that you will be arriving at, what it will be? So VGS minus VTH, you can club together. These two you can club together because these are constants. Okay, so let me write W mu COX 0 to VDS VGS minus VTH into dV. Okay, then minus of 0 to VDS V into dV, and here it is id 0 to L dx. Is this clear? Now W mu COX VGS minus VTH into VDS, because I am integrating dV, minus what it will be? V square by 2 VDS square by 2. Okay, and there is a bracket here, and here it will be id into L, so I am just writing the L here directly. I hope that is not a problem. Okay, so this will be L, so let me write here only, otherwise. Okay, so from here I have arrived at id equals to W mu COX by L. 2 also you can keep outside. Okay, 2 times VGS minus VTH into VDS minus VDS square. This is what the MOSFET's current equation is, and this will be the equation that will come into use for your entire life if you are an analog designer. If you are not an analog designer, then at least till GATE exam it will come into use. Okay, so this is what we arrive at MOSFET's equation. Okay, so I wanted you to see the derivation. Instead, we always keep on writing this equation only. So now from here we have another thing, that W by L is called the aspect ratio. Okay, and here if VDS is very less than 2 times VGS minus VTH. So VDS is very less than 2 times VGS minus VDS. You can see I can neglect the second term, and therefore id will be approximately equal to mu n COX by W by L VGS minus VTH into VDS. Any doubts in this? I've put this condition. right? This condition, this gives you this, right? Now from here what you can do, you can find VDS by ID, which will give you VDS by ID, which will give you R on, which is 1 by mu n COX W by L VGS minus VTH. Is this fine? So there was one question regarding the R on resistance. We will take that. It was in 2011 that they had asked. We'll take it in last, by the end of the class. Okay. So till here, is it fine? So we will see the DC characteristic later on, but just to have a glimpse, if you see, you will get with respect to this ID VDS curve. If you see, okay, so ID VDS curve is something like this. It goes, okay. So for very low values, as we have seen, what we saw VDS very less than 2 times VGS minus VTH. Okay, so this is for some particular value of VGS, this curve will come. So if this is maintained, that means we are in somewhat this region, and you see this region, it is almost linear. That means it works as a MOSFET, works as a linear resistor in deep triode, in triode region, where actually it is a VDS is very less than 2 times VGS minus VTH. Okay, it cannot be just less than. Okay, so I should not say it should be deep triode only. So basically, when VDS is just less than VGS, so there will be these regions: VDS less than VGS minus VTH, VDS very less than 2 times VGS minus VTH, VDS greater than VGS minus VTH. So here it is saturation, here it is, you can say it is a deep triode, but you can say it's deep triode, and it works as a linear resistor. Here it works as a current source, and this is a triode region. Okay. From BJT, the difference is that the BJT works as a current source in active region. Here that region is called saturation region. Okay, so mind that difference, don't get confused. You can take a photo if you want here, then I will go to the next thing, whatever we are discussing. Now we will come to another important topic, which is a channel length modulation, right? From here we arrive at channel length modulation. So what is it? And another, yeah. So till here, is it clear? Like whatever the derivation and everything we saw, it should be. Okay, so it is not very much difficult. Now, we saw that the channel density QD is given as, what was it? COX W into VGS minus V of X minus VTH, right? Now, question may arise that what happens if V of X starts approaching VGS minus VTH, then QD will start approaching 0, right? So now this V of X, this V of X at X equals to L, that is at drain, what it was VDS, right? So that means if my VDS or V of X as for matter, if it becomes greater than equal to VGS minus VTH, the channel density should be 0, right? So what happens is, here in this diagram you can see that they have taken one point x1, right? You have just taken this point as x1. Now at this point, at V of x1, this is equal to VGS minus VTH. That means here the charge is actually 0, right? And therefore now the channel length is no longer at x1. The channel length is now till here, right? The channel length is not present here. So that means the L has now reduced to x1. L has reduced from x1 because at x1 it is 0. So channel length is what? It is varying. So how is it varying? The channel length is varying because VDS, we had applied some VDS there, and that VDS at point x1, or I should say that I have applied some voltage at x1. That voltage at x1 is becoming equal to VGS minus VTH, and therefore the charge is 0 at that point, and therefore the channel length has also shrunk. That means this voltage, whatever it is able to control the channel's length. So whatever VDS I put, it is actually controlling the channel's length, and that is what is channel length modulation. Okay, so here you see Vx2 they have taken, and it is equals to VGS minus VTH, and therefore here the channel charge is 0. Therefore the channel is pinched off here. It is pinched off, and only till here, therefore you are getting a voltage difference, you are getting a charge. But that does not mean that your current will be 0. You can think that oh, QD is 0, that is current is 0. No, you have to remember that this is charge per unit, that distance, right? It is charge density. So what happens is, because of the electric field, there is a constant velocity with which the electrons keep on moving. Okay, and that actually arises the current, and therefore the current, after increasing like this, it will never fall like this to 0. It will not do that. Instead, it will be constant. Therefore, you see this graph. And since this VDS is able to control the channel's length, and the R out, the output resistance here, whatever the resistance is here, is not 0, is not infinity. If the resistance is infinity, it will be a straight line. But it is not infinity. We will see how it comes. It therefore becomes like this. It will be a slightly tapered. Okay. So as R out decreases, it will become like this. And if R out increases, it will come like this. So basically R out is infinity. Okay. So this we will see in DC characteristics more. So I hope this is clear. What is pinched off? How is channel length modulation working here? Okay, and therefore from here we arrive at this equation, that ID equals to half mu n COX W by L, that we have saw that this is VGS minus VTH, VDS minus VDS square, right? So now I am saying that VDS has become equal to VGS minus VTH. Okay, therefore ID is half mu n COX W by L. This is 2 times VDS square, right? Minus VDS square. So this is again half mu n COX W by L into VDS square. And VDS, we saw it is VGS minus VTH. Therefore, always you will find this equation for saturation region. Okay. This is what you get for saturation region. This is also very much used. Okay. And now here I should mention that I should not write L but L dash, because it is not the complete L now. Channel has been pinched off, right? So this L dash will actually be less than the L that we had seen earlier. But normally when you solve numericals, whatever L is given, you take that. Okay. So for understanding purposes, you should know that this is actually a different L than the earlier L. Earlier L means the L which is here. Okay, this L, and here this is L dash, and L dash will be less than L because the channel is now smaller than it was before. lengthwise, right? Now here we also say that the device is behaving, has a square law behavior, and L dash will not be very less than L, it is close to L. L dash is close to L. Okay, and the device is having square law behavior. Why? Because VGS, you will see that it now follows this. This is what VGS is. But you need not memorize it. You need to remember this equation only and this equation. Okay, so here we say it is square law behavior. And the VDS, so VDS, if you see that I have to maintain VDS equals to VGS minus VTH for the MOSFET to operate in saturation region. So this is also sometimes called as overdrive voltage or headroom voltage. Okay, what do you mean by headroom? Suppose you enter a room, okay, and it is very small, like the roof of the room is very near to your head. That means the head to your room's roof is, that space is very less. So that is the headroom you have to stand straight. Okay, so likewise, when we make amplifiers or we make current sources using MOSFETs, if you have something like this kind of a circuit, suppose you are taking output from here, you're giving VDD. So VDD will bias the MOSFET, and this biasing will make sure there is some VDS here. So you cannot just abruptly do it. If the VDD is unable to sufficiently put 3 VDS here, say, okay, all these biasings, if the VDD is unable to do, then your MOSFET will not work. That's why these are called headroom voltages. I'm not going very in deep in this. So these are called headroom voltages. Okay, the same thing will happen for PMOS as well, and there will be a negative sign because of the carrier, we saw that, right? So minus mu p COX W by L VGS, so this will be VSG actually. Okay, let me write VGS minus VTH square, right? So what happens is, my way of dealing with MOSFETs is, so this is my PMOS, right? And this is my NMOS. PMOS, NMOS. So how I take the convention is, I will take this as source, this is drain, right? And here this is source, this is drain, and I consider the current always to be in the positive direction. So the current flowing from source to drain, and there the current is from drain to source. So current flowing from drain to source, IDS is positive in NMOS and ISD is positive in PMOS. Similarly, VSG is positive in PMOS, VGS is positive in PMOS. And therefore, when I take V threshold, actually the VTP is a negative value, VTN is positive value, but when I use it in equations, I always use as mod VTP, mod VTN. Okay, so here if I write, how will I write? ID is mu P COX W by L. Here it will be VSG minus mod VTP square. In this way, there will never be sign mistakes or anything. Otherwise, if you mess up, so always remember this is a difference. Okay, always remember that this is a difference. That means if your say they have said that the gate to source voltage of P MOSFET is, let's say they have given VGS as -5 and they are saying VTP is -1. So never do it like this. -5 -1 is -6. Don't do this. Okay, what you should do is this, the difference has to be taken. So it is nothing but 5 minus 1, 4 volts, or you can say -5 plus 1 minus 4 volts with respect to whatever. It is always with respect to the potentials, that's right. Okay, so it is a difference that matters. Okay, So this is how I take up. When we take questions, this will make more clear. So till here, if it is it fine or not. After this, I will go to the transconductance, and then we will see the body effect quickly and solve one question for R1. Okay, so now obviously since there is a current, there is a voltage you had applied, and there is a current flowing, right? So I got ID, which is actually proportional to VGS into something whatever, right? That means whenever this kind of a situation is there, there is a presence of transconductance, right? Okay, so transconductance is given by Gm equals to delta ID by delta VGS with VDS constant. And if you do this, and this will only come when at saturation, because in saturation only this is happening, right? You are applying a VGS, you are getting a ID which is completely proportional to it, right? So in saturation, we will see it is mu n Cux W by L transconductance amplifier. Okay, so this is what you will arrive at. You will also arrive at two more equations, because if you substitute VGS minus VTH from ID equation, you will get, is there any doubt here from where I am getting this? ID we know, right? ID we knew that we got mu n Cux W by L VGS minus VTH square. So from here I am just substituting the value of VGS minus VTH here, and we will arrive at equation with respect to ID. And from here you will also arrive at, if you substitute W by L, you will arrive at this equation. Three equations. Now when to use what? When to use what? I'll just put it a bit away. Okay. You see these three equations? Now, what will happen? When GM is, you can use any of these equations, okay? Depending on whatever parameters you have been given. Because in gate it will be only numerical answers. So VGS minus VTH. Okay, what is important is the graph. They can ask you objective type questions where they will put the graph and they will ask you the variation of GM with respect to a quantity. Now, if they say my W by L is constant, okay, then what is GM with respect to VGS minus VTH? This they can ask. They can ask like, tell what graph is correct, and that can become a multiple choice question. Which graph is correct? So this will be what? Linear, right? GM varies linearly with VGS minus VTH, having W by L constant. That is more important, very much important. It can be a one-line answer also, that transconductance of a MOSFET is varies proportionally with VGS minus VTH when W by L is constant. So that is a true statement. Like that also they can ask, right? Similarly, W by L is constant, okay? And here in x-axis I have ID. What will happen now? You have to see the second equation, right? Second equation. Equation 2. What will happen? Square law behavior, right? Square law behavior. Again, GM with VGS minus VTH at x-axis with ID constant. Now not W by L is not constant. ID is constant. It will be like this. Why? Because we have seen GM equals to 2ID by. So whatever is constant and whatever is varying will have to be in the same equation, right? You see here, when I was saying W by L is constant, I am putting x-axis this. I am saying W by L constant, I am putting x-axis ID. I am saying ID constant, VGS minus VTH is x-axis. If I say VGS minus VTH is constant, ID is in x-axis. You understand? So these three graphs, you will find it in Razavi's book. You go through it. This can be asked. Okay. So we only need not see that what previous year have asked. We should also see that what can be asked. Okay, so the trend is moving more towards MOSFET is what I am feeling. That's why I thought I should put it a bit in detail. Okay, so if this is clear, then we can move to the second order of effect of body effect. Okay, okay, so let's see what body effect is. I'll quickly tell you. I won't take much time because normally I have seen normal numerical answer type sometimes they can ask. Okay, so body effect is, as I had mentioned, that MOSFET is a 4-terminal device. Okay, and this is P substrate. Okay, so now what is happening? Suppose here there is a depletion region. There is no inversion yet. Okay, depletion region. That means Vg is less than Vth. Depletion region is there. Vg is less than Vth. Now what is happening? I am putting a voltage Vb which is less than 0. What will happen? Whatever the holes are there, they will get what will sorry, I am putting Vb greater than 0. If I put Vb less than 0, nothing will happen. But if I put Vb greater than 0, what will happen? Actually, Vb less than 0 will also happen, I will tell you. So Vb greater than 0. So Vb is more positive. So we are in depletion region. We are not in inversion region because Vg is less than Vth. There is no current in the device. Negative ions are there which are immobile in the channel. Channel is not yet formed actually. So when I have a Vb positive, what will happen? The electrons that are free here, they will find a force and they will try to go towards this, right? And now with this positive Vb, if I now try to put a gate voltage to bring it to inversion region, I will have to do more work. That means more Vg will be needed to on the device. And therefore, we can say that the threshold voltage has increased. So that is how Vb actually leads to increase in threshold voltage. Now if Vb is less than 0, what will happen? It will repel, okay, and kind of help in reducing the VTH. But that also is not very good. Okay, so we don't want the device to turn on suddenly with a very small application of Vg, it just turned on. Okay, that also we don't want. And we don't want Vg to be very high, that the MOSFET is not turning on only. So we will need more VDD, that means, right, to turn on the MOSFET. So that we don't want that also. So there is a balance that should be there. Okay, so the formula is given by VTH equals to VTH 0. VTH 0 is the actual threshold voltage plus gamma. Gamma is a body coefficient. Okay, so I'll tell you what the value is. 102 phi f plus VSB. Phi f is a work function. Okay, so all these values will be given to you and then you will be asked a question. Okay, or you can be asked a theoretical question also from here. If a numerical question is asked, then if straight away these parameters are given, you can just find out and give the numerical answer type. If it is an objective and a lot of things are given and you have to find something and something and something, you should just skip the question. If it is a 2 marks question, you should just skip it because you don't know what else things are have to be found. So you have to judge the question. Okay, but if it is straightforward thing, numerical answer type, you should go with it and you should apply your concept and do it. Okay, so the body effect is also called as backgate effect. Okay, it is also called as backgate effect. So till here, is it fine? Is everything clear? We are almost out of time, so I will just quickly do a Aron question which was there in 2011. Okay, so please don't ask for notes. I won't be able to give you any notes because these are very much rough work. So if someone sees that, they might think that I have written something wrong also somewhere, because I'm in continuation of writing, right? So notes should always be proper. So if you want, you can go to Razavi's book. Everything is from Razavi. Okay, I'm explaining that only. Okay, and Razavi's microelectronics. Let me see what is the book. Oh, design of analog CMOS. This book you can refer to. Okay, so not too much is needed. So let me go to the question. This was a 2011 question. Someone sent it to me. GATE 2011 and 2012 papers were one of the toughest papers. GATE 2012 especially for ECE. I think the highest marks was 63. So you can compare. Now it is like 95, 97 normally goes, right? And but the highest marks was I think 67 if I'm not wrong, or 72, something like that. So it was a very tough paper. GATE 2012. This is from 2011. Okay. So please read the question first and take a snap. So the figure, I hope it is clear. I'll just write it. This is Tox P plus N. Okay. This is VGS. The gate, source and drain. Okay. Okay. They've said that the channel resistance, R channel, is 600 ohm. Okay. So this is not directly an R on question. It is mainly, you can see that this here you will be using the semiconductors concept, what you normally read in the semiconductor chapter. Okay. So our channel is 600 ohms. Okay. Where the full channel thickness is 10 micrometer. Okay, built-in potential at this case is -1 volt. Okay, so they are saying that when VGS is 0 volt, channel is depleted by 1 micrometer on each side. So W depletion total will be 2 micrometer, right? 1 micrometer each side they have depleted. That means here and here, these two depletion is 1 micrometer. I just draw it in the diagram. Here there will be a depletion region. That is what they are talking about. Okay. So after this, W depletion is 2 micrometer. Okay, and due to the built-in voltage and hence the thickness available for conduction is 8 micrometer. So TCH has now become 10 minus 2. This is when VGS is 0 volt, right? The first question is channel resistance. Find the channel resistance when VGS is 0 volt. So VGS 0 volt, they have told you what Tox is, what is happening to the this channel's thickness, right? Channel's thickness. So TCH, not TOX, TCH, right? Now, how is the resistance related to the channel, channel's thickness? So rho is R is rho L by A. To thickness, it is related inversely, right? So RCH1 by RCH2 will be equal to TCH2 by TCH. Now RCH1 is given as 600, RCH2, TCH2 is 8, TCH1 is 10. Then what is RCH2? It is, so you see they had given n channel JFET, right? N channel JFET, which is not in syllabus, I know. But the question is actually not at all related to the JFET thing. It is just basic, and it is semiconductors. So they can frame a similar question with respect to MOSFET also. That is possible. They can ask from the depletion capacitance. Okay. Now, second, VGS is minus 3 volts. So at 0 volt it was fine because they have already given what is the depletion of the thickness. But now when VGS is minus 3 volt, what is the depletion of the thickness? That you have to find first. Now you see this is the depletion width formula that you had learnt. And the depletion width is under root V naught. That is how it varies with the built-in potential. That means built-in potential will be W square proportional to W square. Right? So now VGS is minus 3 volt. Built-in is what? Minus 1 volt. Right? So when VGS was 0 volt, built-in was minus 1 volt. Built-in, because built-in is constant, right? That is the built-in potential that we had seen. It is constant, minus 1 volt. What will be the total voltage therefore? So I am writing at V2 minus 3 minus 1 minus 4 volts. V1 0 minus 1 minus 1 volt. This is the total voltage. Don't subtract it and make it plus. The reverse biasing is increasing the depletion voltage region. So increasing in the depletion voltage also. Increasing in the reverse voltage. Right? So minus 4 volts. Okay. So now we just saw that it's directly proportional to W square. So V2 by V1. W2 square by W1 square. Right? Minus 4 by minus 1. W2 square by W1 square. 4 times W1 square is W2 square. This implies W2 is 2 times W1. This we have understood. Okay, fine. Now what is W1? It is the depleted width, which is given as 1 micrometer on each side. Don't take 10 microns. 10 microns is the channel's, the total thickness of the channel. Right? So this is the depletion width. That means a new depletion will be 2 times of it, 2 micron. That means this was 2 micrometer total because 1 micrometer on each side, and this is 2 micrometer on each side. That means 4 micrometer total. Okay. Therefore, what is the channel length now? What is the channel's thickness now? Channel's thickness is original thickness 10 micrometer minus 4 micrometer, 6 micrometer. This is the effect of VGS minus 3 volts because you have increased the reverse bias and therefore the depletion width increased by 2 times on each side and therefore your effective channel reduced. Earlier it was TCH is 10 micrometer minus 2 micrometer, 8 micrometer, which was already given in the question. VGS 3 volt, 0 volts. Is this clear or not? Did you understand this? Because after this it is easy. R will be nothing but what? The same formula you have to use, RCH1 into 10 by 6. And this will give you 1000 ohms. The channel resistance has also increased. Because the channel's thickness reduced, channel's resistance increased, the current will reduce. Because depletion width is increasing, you are increasing the reverse bias. From numerical also you understood the theory. Is this clear? Or should I go it once over again? So in the question, VGS is 0 volt was given. They have given a channel resistance and they have given some built-in potential. And they said that, okay, there was a depletion in, you know what, there was a depletion in both the side, 1 micron, 1 micron. So now find what is the new channel resistance. So you saw that, okay, 1 micron here, 1 micron there, add it up, 2 micron, subtract from the channel, 8 micron. I can directly find the resistance. But in next question, they turned it. They said no, it is no longer 0 volts. It is now minus 3. That means I am increasing the reverse bias. And if I am increasing the reverse bias, then I have to find the new voltage. And if I find the new voltage, why I need the new voltage? Because I now need to find the new width. So if I find the new voltage, from there I find the new width. And when I find the new width, I now know that whatever was earlier, in 0 volts it was 1 micron here, 1 micron here. For minus 3 it will be 2 micron here, 2 micron here. They have used the VGS minus 3 cleverly only because that you should get this kind of result, W2 equals to 2W1. So 2 micron here, 2 micron here, total 4 micron is now depleted. So 10 minus 4 is 6 micron. You put in the value, you get the answer. You see the channel resistance has increased. Earlier it was 600 ohms, 750 ohms. So the actual channel resistance is 600 ohms. If it is depleted, when VGS is 0 volt, it depletes, becomes 8 micron. And then it depletes when VGS is minus 3 volt, it depletes to 6 microns. Okay, very interesting question. Okay. And it had nothing to do with JFET or anything. It was a simple question of resistance and your knowledge with the depletion layer. Okay. So with this I end up here. Next class we will see the MOSFET's DC characteristics. Okay. And also AC analysis we will do. And then if time permits we will take up questions. Otherwise in next we will take up questions. Okay. Okay then, please join on time so that you can understand everything that is going on in the class. Okay. Okay. Bye then.